Hi. I want to solve this crazy problem involving the ladder. Suppose a 2-meter ladder leans against a 1-meter high wall. What is the maximum horizontal distance a ladder can extend beyond the wall while keeping the foot of the ladder on the horizontal ground? So these problems, this is an applied optimization problem. We're trying to maximize something. These problems very often come down to, first of all, understanding, translating what the words in the problem are sort of asking you to do, describing the situation, and using that description to form an accurate model inside of your head or on your paper of what's actually going on. Here's what I believe is going on. I'm pretty sure I'm right. We have a horizontal ground. We have a 1-meter high wall. This is 1 meter. And then we have a ladder, which is sort of, at an angle with respect to this wall. We have this kind of situation. So there's the wall there marked with 1 meter. And then we've got this ladder being, of course, 2 meters high, long, rather. And what we would like to understand is the overhang, horizontal overhang of this ladder. So we want to understand and maximize that green segment there. We want to maximize the length of that green segment. Let's call that green segment there H. We want to maximize that, okay? Now, we understand that, as this ladder kind of slides along the wall, let's say, here's the ladder, here's the wall, and here's the ladder. Well, this is not a great example. Is there something smaller I can use? Sure. How about this thing? We understand that as we have this wall sitting here, and we have a ladder leaning on it, that, the how can I, there we go. Okay. That as we sort of shift this ladder around, maintaining its foot on the ground, we're going to see varying horizontal overhangs happening. Yes? Varying horizontal overhangs. And so what we want to do is maximize that horizontal overhang. How are we going to do that? Well, what we should do is try to relate H there to some quantity in the problem that we can get a handle on. Now, one thing that we don't have marked in our picture is the length of the ladder, yeah? The length of the ladder, of course, we know is 2 meters. So this distance here is 2 meters. I know you can't see it. That's that distance there. So what I'm going to do is I'm going to declare... so let me back up. If you look at this problem from a geometric point of view, you should notice something very significant. And that is that there are a pair of similar triangles in this problem. Do you see them? In fact, they're right triangles. There's a right triangle here and a right triangle here. They are similar to one another. Okay. In fact, let me just give them names. I'm going to call this triangle here, the top triangle, I'm going to call that T1, and the bottom triangle T2, just so we can refer to them easily with one another. That top triangle is T1, bottom triangle is T2. These triangles are similar. Okay. So we would like to somehow exploit that similarity to write down an equation for H, right? Because H is the thing that we're trying to maximize, so we want an equation for it. We just have to decide what variable we are going to let H depend on. Maybe more than one variable. I would say that we should use the fact that that ladder there is 2 meters long to figure out the proper value for H. So this is what I'm going to do. You might do it differently. Who knows? I'm going to let X denote the distance, the amount of ladder from the ground up to the tippy top of the wall. Okay, that's going to be X. Now, if that's X, we also know what the distance from the tippy top, we know the distance from along the ladder, how much of the ladder goes from the top of the wall up to the top of the ladder. Does that make sense? we in other words know the hypotenuse of T1. The hypotenuse of T1 is 2 minus x. Don't you agree? Because the whole thing, after all, is 2 meters. So we have this kind of situation here. Okay, cool. Now, if we're going to use similar triangles, then we know that ratios of corresponding edges in similar triangles are equal, right? Because a similar triangle is related to some other similar triangle by just some kind of scaling operation, some kind of multiplication by some constant. So I have here h, which is the bottom leg of T1. I think I would like, and I know the hypotenuse of T1. I know the hypotenuse of T2. I would like to know the bottom leg of T2, because then I could set up an equation coming from the similarity of these triangles, which will allow me to get a handle on h. So see if you can't figure out what that is. Maybe pause the video here and then see if you can't figure that out. I'm going to go ahead and do that. Of course, what we're going to use is Pythagoras. We're looking at Pythagoras in T sub 2, in the T2 triangle there. And to find that third leg of that right triangle there, we look at the square root of x squared minus 1, like this. Really, we can think of it as a minus 1 squared if we want to, but that's good enough. Okay. And if we have that, then we know by similar triangles that h over the square root of x squared minus 1, h over the square root of x squared minus 1 is equal to the ratio of the hypotenuses of those similar triangles. So the hypotenuse of the hypotenuse of T2 is 2 minus x, while the hypotenuse of T, did I say that wrong? The hypotenuse of T1 is 2 minus x, while the hypotenuse of T2 is just x. Yeah, okay, so x. So this is the similar triangles equation that I get. Right? This comes from the fact that I have similar triangles. Okay, so now I can solve for h. Hi. So what I get is that h, and I'm going to is going to be equal to 2 minus x over x times the square root of x squared minus 1. Okay. All right. Now this is the quantity that I want to maximize. This is the quantity I want to make as big as possible. Now, do I need to consider this for all x? Oh, heck no, right? There are a lot of values of x here for which this thing is not even well defined. For example, look at that square root there. And suppose that x was 0. Well, we would find ourselves taking the square root of a negative number there, and we know that's not well defined. In fact, it makes a lot of sense, right? There are only certain values that x can take on. And if you look at the picture, it sort of makes sense. X is the sort of portion of the ladder that's sort of below the vertical level of the wall. So there are a couple of extremes that we can sort of talk about. If this is the ladder again, right? And sorry, if this is the wall, rather, and this is the ladder, then one extreme that we can discuss is when the ladder is completely flush up against that wall, like this. If that were to be the case, then what would be the value of x? Well, the portion of the ladder that would be up against the wall would be 1 meter, because the wall is 1 meter, right? So the smallest that x could be is 1. What is the biggest that x could be? The biggest that x could be is when the very tippy top of the ladder is touching the wall, like this. That is occurs when x is equal to 2. Okay, so we're going to maximize this function h when x is between 1 and 2. This is we're only considering values of x between 1 and 2, in other words. Okay, and that's going to be an important thing for us, because when we have a function on a closed and bounded interval, The only way that well, first of all, we know that the absolute minimum and maximum exist because this is a compact interval where we have a continuous function on a compact. Sorry, you don't know the word compact, on a closed and bounded interval, and so we know that an absolute max and an absolute min exist. Okay, so we know that. What is the second point? It could. So we know that the absolute extrema have to occur either at the endpoints of that interval or at a critical point for the function. Okay, so what we do in order to find the maximum and minimum of a function on a closed and bounded interval is find the critical points of the function and then evaluate the function at those critical points and also at the endpoints. The largest value that we thus obtain will be equal to the absolute, will correspond to the absolute max, while the absolute min will correspond to the smallest value that we obtain in this manner. Okay? All right, so let's find h prime. Yes? H prime. To find h prime, I'm going to use, if you look at it, there's my h. To find h prime, I'm going to use, what do you call it? The product rule. So I'm going to let u equal 2 minus x over x, and I'm going to let v be equal to the square root of x squared minus 1. Okay. Now u prime, I need the quotient rule for. So I'm going to use that. So u prime, I'm going to take the derivative of the top, which is -1, times the bottom, so that's negative x, minus the derivative of the bottom, times the top, which is 2 minus x. And I'm going to divide this whole thing by x squared. So this is what I get. Let me see if that's right. So the derivative of the top is -1 times the bottom is x, negative x, minus the derivative of the bottom, which is just 1, times the top, which is 2 minus x. Note my parentheses. Yeah, if I leave those off, I'm dead wrong. And then I have x squared. And okay, good. I like it. And now v prime. For v prime, we use the chain rule. We know that the square root of blah, the derivative square root of blah, with respect to blah, is 1 over 2 times the square root of blah. You can use the power rule there to figure that out. But when you're taking a derivative with respect to x, you have to multiply 1 over 2 times the square root of blah by the derivative of blah. So this is makes it pretty easy. This is just going to be 2x over 2 times the square root of x squared minus 1. Yes, 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 yes. Very good. So those 2's die, and I like killing 2's. I like simplifying things at the outset. So this is the same as x over square root of x squared minus 1. Great. And over here, for u prime, I'm going to simplify that as well. It is in my interest to do so. What the hell? I can't. Can you see that? There's u prime, right? No, god damn it. Right there. There's u prime. And now I'm going to massage that a little bit, because this becomes minus x minus 2 plus x divided by x squared. Oh geez, I realized quotient rule is really silly here. I'm not thinking very clearly. Anyway, we have minus 2 over x squared. That's our u prime. Can you hold that? All right, so now we quotient rule this thing. H prime is equal to u over v prime, which is equal to u prime v minus, wait, what am I doing? No, my bad. It's not the quotient rule that we do on h prime. It's the product rule, adoy, right? H is the product of u and v. So we have uv prime, which is u prime v plus v prime u. So then working that out, u prime is negative 2 over x squared. V is square root of x squared minus 1. Plus v prime, which is x over square root of x squared minus 1, times u, which is this mess here, 2 minus x over x. And this is where I'm at. Now what I want to do is I want to work with this thing. I want to, in particular, like set it equal to 0, do all sorts of things like that. So what I'm going to do is simplify this thing. Okay, so this is a good algebra exercise. This is a very good problem for a lot of reasons. I note that down here in the denominator of this first term, the denominator of this first term is x squared, yes? While the denominator of this term over here is x times square root of x squared minus 1. So if I want to make a common denominator, I think what I'll do is I'll multiply the first term, top and bottom, by square root of x squared minus 1. And I'll multiply the second term, top and bottom, by just x. Let's do it. So I'll multiply the first term by square root of x squared minus 1. If I do that, I get negative 2 times x squared minus 1 divided by x squared, square root of x squared minus 1. So this is, my pen is goofing up. This is what I get for the first term. I'm not done yet. That's just my first term. And then for my second term, I'm going to multiply top and bottom by x. So I get x squared times 2 minus x divided by x squared times the square root of x squared minus 1. This is nice. Very nice. We all okay so far? Okay. So and then we keep moving. I'm going to combine those two terms together. Remember, this is h prime. So what I get is negative 2x squared plus 2 plus 2x squared minus x cubed divided by x squared times the square root of x squared minus 1. This is me just combining the terms together, making a single fractional expression. And now we see this lovely thing happening where the x squared terms cancel. So this is equal to 2 minus x cubed over x squared times the square root of x squared minus 1. And this is the expression for the derivative of the derivative. This is the expression for the derivative. Gosh, I feel a little weird about this. Okay. Something feels off to me about this, but let's just persevere. No, maybe it's okay. I don't know. Something feels weird, a little bit off to me, but okay, whatever. I can obsess about that on my own time. Okay, great. So here's our expression for the derivative. Now we want to figure out when this thing is undefined, when it's 0. So it's undefined when that numerator there, that denominator there is 0. That happens when x is equal to 0, which we can ignore because remember x is only between 1 and 2 for us. And it also occurs when the thing under the square root there is well, I guess when it's 0 or it's negative. The 0 is a problem not for the square root, but because then we'll have a 0 denominator. So that's not good. When is it 0? The thing under the square root there. It's 0 when x is plus or minus 1. Yeah, I hope that's evident without too much hemming and hawing. And when is it negative? Well, if you think about it, it's a parabola. Its zeros occur at x equal to plus or minus 1, so it's going to be negative in between those two roots. So square root of x squared minus 1 is undefined for x between negative 1 and 1. Fortunately, we can ignore those, because remember, x is only between 1 and 2. See right there? That's the thing that we said at the very start. So we can ignore those. Great. So the only thing we need to think about is when this thing is equal to 0, when this first derivative here is equal to 0. So what we're going to do is solve 2 minus x cubed equals 0. And that's an easy thing. This just implies that x is equal to 2 to the 1/3 power. Is that not lovely? Isn't that lovely? Now, how do I know that this corresponds to the absolute maximum? I mean, so we know that the absolute maximum has to occur at the endpoints of this quantity here, of this x, the endpoints of this interval, sorry, my bad, the endpoints of this interval, or at a critical point of the function h. But if we look at this thing and we think about what's going on at the endpoints, what happens when x is equal to 1? Well, isn't it pretty obvious that h is 0? Because x is equal to 1, remember, corresponds to the situation where the ladder is completely vertical and flush against the wall. So there's not going to be any horizontal or overhang. So h is 0. How about when x is 2? Well, when x is 2, the tippy top of the ladder is sitting up against the wall and is at the top of the wall, right? In other words, there's no T1 there. T1 is like an empty triangle in some sense, yes? So h is also 0 when x is 2. So all we need to decide, in order to decide if this thing is this critical point here is a absolute maximum, is whether or not, if we plug this number in to h, will we get a positive answer? What was h again? It was this thing right here. Okay? Now, the cube root of 2 is obviously going to be smaller than 2. So 2 minus x is going to be positive. Cube root of 2 is positive. So that x down there in the denominator is also going to be positive. And the cube root of 2, well, how can I say it? It has to be bigger than 1, right? Because we're going to cube it and get something which is equal to 2. So it can't be less than 1. It's not 1 either. That doesn't make sense. So we can see that the square of the cube root of 2 is going to be certainly bigger than 1. And then we have the square root of something. So that's positive. So in other words, we know that just on the fact that I don't know the exact value and I don't care to find out. What I know now is that when x is equal to 2 to the 1/3, that h is positive. And since this is a critical point, and since h is 0 at the endpoints of the interval, I know that x equal to 2 to the 1/3, that corresponds to the absolute maximum of this function, right? So we know that h of 1 is 0. We know h of 2 is 0. And we know that h of 2 to the 1/3, I don't care to compute it, is positive. So this is me evaluating h at each of those 3 points. Therefore, x equal to 2 to the 1/3 is the absolute maximum. Cube root of 3. So that's the configuration of the ladder. You want to have the cube root of 2 meters of the ladder below the top of the wall. And the remaining portion, 2 minus 2, the cube root of 2, above the wall. And that will maximize the horizontal overhang over the wall. How nice, right? All right, that's enough. This was a hard problem. Would I do this to you on an exam? Almost certainly not. But if you understood every single step, then you understand these problems, because this is a hard one. The hardest part has got to be the very first step. So please try to understand my rationale for why I developed a problem in this manner. I think that's important and useful for you. By the way, you might want to, and this is the thing that's kind of hanging me up a little bit. There's something, it seems like, the thing that's bothering me is that it seems as though I'm not sure that the length of the ladder really came into play. What do you think? If instead of a 2 meter long ladder, let's say I had a 200 meter long ladder, would the answer here change? That's an interesting question. How could we detect mathematically whether or not the answer would change? I'm kind of inclined. No, I think that the answer should change, shouldn't it, right? I'm pretty unsure. No, the answer will change. Yeah, the answer will change. Yeah, almost certainly. Yeah, yeah, yeah. Right. um, I think so. Anyway, maybe I should have not mentioned that part. This problem is fine as it is. Okay. See you later. Bye bye.